Derive the equation for centripetal force. So let's consider an object going in a circular trajectory. We're going to consider that sometime it can be identified by a vector from the origin to a location, and that vector is the vector r, which is a function of time. Now, after some time has passed, that object has moved around that circular path and is at a new position that can be identified by a vector r2, which would be r sub t plus some dt, some small change in time. And so this is the location 1. This is, you could say, position A and position B. I'm going to change the expressions here just to make it a little bit easier and less crowded. So the initial position is r1, vector r1. Second position is given by vector r2. This is the initial position. This is the position at some time dt later. So it's a uniform circular motion, so we know that r1 is equal to r2. That means the magnitude of those two vectors are the same. And we also know that because it's moving, it has a speed and it has a direction, so it has a velocity. So in position 1, it was moving in this direction. And as you know, in circular motion, you're always moving tangential to the circular path. Okay, and then at some time 2, it's moving maybe like that. I'm not sure my two vectors are the exact same length, but they should be, because again, this is uniform motion, so the speed is not changing, and the distance of the object from the center of the circle is also not changing. Now, because this is tangential motion, the angle between the r vector and the velocity vector is always 90 degrees. So let me label those two. This is b1 vector. This is b2 vector. Okay, and so during this time dt, I'll just put it here, elapsed time, is dt, some infinitesimal amount of time. In that amount of time, the object went from position A to position B, and it underwent a rotation over an angle d theta. Okay, we're going to look at this a little bit more closely. Here we are again. I'm going to expand that so it's easier to show the next things I want to talk about. Okay, so we have this relationship between the vectors. Again, we also know that v1 is equal to v2, meaning the magnitudes are the same. It would be interesting to know what exactly is the vector that would change v1 to v2. So as you know from other lectures, if you have two vectors, let's say I have vector A, I'll write this over here. Let's say I have vector A in this direction, and then I have vector B in this direction, I would add them up, and so then I'll get a vector C, which should be this vector, right? So in this case, you see that what I have is that vector A plus vector B equals vector C. So you can consider that in order to transform vector A into vector C, all I have to do is add a vector B. Okay, so let's see if we can use that to help us understand what's going on here. I'm going to try to take this vector and put it here. Alright, so I'll attempt to draw it exactly the same. I don't think I succeeded. Let's try it again. More or less. Okay, so that's just vector B1 again. Now, what I need to find is this vector that transforms vector B1 into vector B2, which should be that one right there. Meaning, if I add this vector to this vector, then I would get vector B2. Okay, so what vector is that? Well, I could call it vector dB, because this is the vector that changed vector 1 into vector v1 into vector v2, meaning it's the one that changed my velocity 1 into my velocity 2. So it's a vector that represents a change in velocity. Alright. And again, the magnitudes of the vectors are the same. The direction is what's changing. So that vector is vector dB. And what do I know about vector dB? Is that it's a change of velocity. Well, that's going to be an important point. So what do I know about velocity? Well, I know that if I have a displacement, let's say x, which is a displacement, then I take the derivative of x with respect to time, and I get a speed. Now, if this is a displacement, now that is a vector, so then this is a vector, and so that gives me a speed. Now, what causes a change in speed? Well, an acceleration causes a change in speed. So then I also know that dv dt is equal to v, from which I can gather that A equals dv dt which means that dv is equal to a dt. Okay, so I have that. Now, what other thing do we know? We know that for infinitesimal displacements, say for instance, here where I have a segment, let me draw that again. Is it still? Yeah. Say here I have an infinitesimal displacement. I'm not gonna worry about the speeds there. I just know that I have a displacement from point A to point B. This trajectory here, I can call that trajectory S. So S would be that circular displacement, and so then S would be equal to R d theta. And if I take the derivative of time of S, I have ds dt is equal to R d theta dt. Right, this is also a speed or a velocity if I have my vectors there. Okay, so then from here I can gather that d theta dt is equal to b over r. Let me put a square bit around these important equations. So we know this. We know this. And we know this, which is what I explained there. Okay. So let's put all of this together. There's one more thing that we can notice, is this thing that we applied right here. Well, we can apply it here as well. But in order to apply it there, we would need to know what this angle is. Let me put it in red. There's an angle here, and this one we don't know what it is, at least not yet. So what is that angle? Well, let's notice what happens when I just extend this line here. I'll try that again. Okay, basically there. Well, so that I have a 90-degree angle right here, just like I have it right here. So that's a 90-degree angle. Now, let's extend this line on which B1 lies. Okay, so what do I know about that? What I know is that okay, well, that's not good. Okay, what I know is that this angle is 90 degrees and that this angle here, I'll call it angle lambda, has to be equal to this angle lambda. I'm not gonna use lambda, let's use another letter, angle F. that angle has to be equal to that angle, and that this theta plus f has to be equal to 90 degrees for two reasons. One, here it's the inside angles of a triangle, and they always add up to 180 degrees. So you have 90 plus these two has to be equal to 180 degrees. That means that these two angles have to add up to 90 degrees. That's reason number one. As if that wasn't enough, I see here that I have angle F and my unknown angle, and they have to be equal to 90 degrees because this line is perpendicular to that line. And I even have it noted right there, that's a right angle. So if I have that this theta plus f has to be equal to 90 degrees from looking at the inside angles of this triangle, and I also have that f plus question mark has to be equal to 90 degrees because these two angles add up to 90 degrees, then it becomes clear that this unknown angle has to be d theta, because f is equal to f and 90 is equal to 90. I guess I'll use, and I'll call it an angle alpha. So that angle alpha really is d theta. And again, I can use this right here that tells me that S is equal to R d theta. And apply it here, and instead of R I have B. And so I can see from this that dV also has to be equal to V d theta. Okay, let's put a square on that. Alright, so I got three very important equations now. Let's give them a name, and I call this equation 1, equation 2, and equation 3. And let's put them together. First, we can see that dV has to be equal to dV. That means that V d theta has to be equal to A dt. So putting equation 1 and 3 together, means that V d theta is equal to A dt. That is also going to be equal to the magnitude, so I'm just going to worry about the magnitudes. Alright, now from here I can solve for A, and so then I have that A must therefore be equal to B d theta over dt. Okay, and notice here I already have what d theta dt is equal to. And so now I add equation 2, and so this becomes A is equal to B times B over r. I'm gonna make myself a little bit more space here. And so that just simplifies to v squared over r. And we have proven thus that the centripetal acceleration is equal to v squared over r.